Okay, so welcome back, everybody. Um, so, uh, Last time I basically finished what allows us to lead into the last chapter 13 topic, which is Lagrange multipliers. Now, Lagrange multipliers are the thing that are necessary to actually answer these optimization problems when we are trying to optimize on a closed and bounded region. Okay, and so that is exactly what we're being asked to do. Let's do the following example, which is a very nice, uh, instructive example that shows exactly why Lagrange multipliers are needed in the first place. So let's pick a region R that is really simple. Okay, so one example of a really simple region R is unit square. Okay, so let's pick a region. We'll call it R. Our region is unit square in the plane. So here's the xy axes. We'll say that our region R is unit square in the plane. Right here's 0. So this is our region R. Okay. All right. So I'm not going to shade it, or else it will. Well, maybe I'll do it in a different color. Yeah. So maybe that will make it look not as confusing there. Okay, so here's my region R. Okay, now the problem is to find the global max and min for the function xy minus x squared, right, on R. So find the global max and min for f on R. Now, there's something to say here, first of all. So first question, maybe before I do anything, what does the max-min theorem say about f? So what does the max-min theorem say about this function? Well, this function is xy minus x squared, so it's a polynomial thing, so it's automatically continuous, right? Everywhere. It's continuous everywhere on the plane. The graph of this function, of course, lies above this region R. That's all we're considering. So my graph of the function lies above R. I don't know exactly what it looks like, right? But I don't have to. That's the strength of these methods. So the graph of this thing lies somewhere above or below R, right? It could dip below R here. I'm not totally sure. But so the graph is either above or below R. Maybe parts are above, parts are below. What does the max-min theorem say? So it's continuous because it's polynomial, and R is a closed and bounded region. So f is continuous on R, and R is a closed and bounded region. What does this mean? The max-min theorem says a continuous function on a closed and bounded region has both a global max and a global min. So f has both a global max and global min. All right, so now it's just a question of actually finding those things. So they're somewhere on R, I just have to find them. Okay, now from what we said last time, where do I look? All right, so second question, right? Where can these global extrema for f occur? Well, there's only two options. They either occur at a critical point on the interior of R, right? That is, they happen at some critical point in R, or in the interior of R. Of course, as I said last time, a global max or global min is going to happen at a either a relative extreme value in the interior or on the boundary. But I can make it an easier statement and just say it's going to happen at some critical point in the interior or somewhere on the boundary, right? So where can these global extrema for f occur? Either at a critical point in the interior, or somewhere on the boundary del R. Well, what is the boundary of R? The boundary of R is this square, right? Here's my boundary. Well, my boundary is this weird non-smooth curve, right? A square, thinking about that square as a curve, this is a curve that has corners, right? It's not smooth at these corners. So this is a piecewise smooth curve. Now, again, just to, point this out, this is a lot more complicated. Even in this example, it's a lot more complicated than what you would have done in Calc 1, because what you would have done in Calc 1, your boundary, right, would have just been 2 points, so you could just plug those in. Here, my boundary has infinitely many points. I can't just plug in infinitely many points, so I'm going to have to do something different, right? So in this case, I have a piecewise smooth curve, and typically the way that I deal with piecewise smooth curves is I break them into their smooth pieces, right? So I'm just going to start somewhere, so I'm going to label this the first piece, and then I'm going to go counterclockwise here. So L1 is my first piece of the curve, that's this one. Okay, and then L2 would be the bottom, L3 would be the right side, and L4 would be the top. Okay, so that's how I'm splitting the boundary of this region. Okay, now, where can these global extrema for f occur? Either at a critical point in the interior, so that's one place. Checking that won't be a problem. I can do that with all of the stuff I did in 13.8. I can do that with all the stuff that we did for the second partials test, right? Or somewhere on the boundary of R. Okay, so that's the bit that's going to require a little bit more work. So let's get to this. So here's my function f xy minus x squared. So the first thing I'm going to do is checking critical points in the interior. So first thing is to find critical points for f. And to do that, of course, I take x and y partials. I can go ahead and do that here. So what's the x partial for f? So the x partial for f is x partial of xy is y. And the x partial of minus x squared is minus 2x. Okay. And the y partial of f is, the y partial of this first term is x, the y partial of the second term is 0. So that's it. Okay. All right. Setting both of these equal to 0. Well, maybe I'll do it on the next page where I have more room. Okay. So setting the gradient of f xy equal to the 0 vector. What does this give me? This tells me that the x partial, which I found to be y minus 2x, is equal to 0. But also, the y partial is equal to 0. So this is these are the two equations I get. Okay. And so, if x is equal to 0, plugging that into the first equation, this means that y is equal to 0. Those are the only possibilities, and so 0, 0 is the only critical point. It's the only critical point of f on R. It's actually the only critical point for f, period. It doesn't even matter what R is. Okay. And in fact, it barely makes the cut, right? It barely makes it on R. Where is 0, 0? It's right here. Right? So this function f actually has no critical points in the interior, its only critical point is on the boundary. It's on the corner right here. And so actually, this whole analysis would have found our global max or min, even if we had never considered the interior, even if we had just restricted ourselves to the boundary. That's not always going to be the case. You can imagine a function sitting over this that's like a hill, and its peak is right in the middle of R, right in the center of R. That could absolutely happen. You could have a valley whose, maximum depth is right in the middle of R or somewhere else in R. So that's not always going to happen. But in this case, actually, everything we're going to be interested in happens on the boundary because the only critical point happens here. Okay. Now, we weren't asked to find any relative extreme values, so we don't have to go through all of that. We're just looking for the global max and min. Okay. And so now we have to do some kind of analysis on the boundary to figure out what's going on. Well, I've already kind of suggested what should happen here. You should split this up into these 4 pieces and then consider each piece separately. Okay, because this thing is going to be slightly simpler depending on which piece it's on here, right? So let's consider the L1 piece first. Okay. So what does f look like on L1? So just to bring that back for a second. L1 is this little strip. Okay. On this little strip, what's changing and what's staying the same? On this little strip, this is a strip of the y-axis. On this y-axis, x, of course, is 0 the whole time, and y is changing, right? So on L1, x is equal to 0, and y is between 0 and 1. Okay. All right. So, what does this mean? If x is equal to 0 on L1, and y is going between 0 and 1, our function f of xy is xy minus x squared. But x is 0 on L1. So what does this become? 0 minus 0 or just 0? So f of x is identically 0 on L1. It is just the function f equals 0. Okay, on that entire strip. So on this entire strip, my function is 0. Okay, so both max and min values of f on L1 are 0. What's the idea? What am I doing here? What I'm going to do is I'm going to find the max and min of f on each piece, right? And then I'm going to compare all of those possible values. Since I know that the global max or min for this function has to happen on the boundary, then finding the largest value it can attain on the boundary is its max, and finding the smallest value is its min. Okay, but on that piece, both its smallest and largest values are 0. In fact, its only values are 0. Okay, so that's simple enough. What about on L2? This is the bottom. Well, on the bottom, here, y is 0. This is a piece of the x-axis. So y is 0 here, and x goes between 0 and 1. Okay, so y is equal to 0, and x is varying between 0 and 1. Okay, and so f of xy is xy minus x squared. X is just varying between 0 and 1, but y is 0, and so this term goes away, so this is minus x squared. Okay, on L2. Well, as x varies from 0 to 1, what is the largest value of f on L2? So max on L2, it happens where? Maybe I should just say max value so that we're actually comparing the values. Where's the maximum for f on L2 going to happen? Well, this is minus x squared. This is always a negative except when x is 0. So the largest value this can attain happens at x equals 0, and it's 0. So max value on L2 is 0. What's the min value? The min value, of course, occurs when x is largest on L2. So the biggest x gets on L2 is 1. And so this min value is minus 1. Oh, I already said on L2. Okay. Now, it is nice to track where this happens. So this one happens when x is equal to 0. And this one happens when x is equal to 1. Okay. All right, and so we've already found, yeah, that's good. I saw you all in chat post the answers here. So we've already seen that the two values of f so far that have sprung our interest is 0 and minus 1. So we already know that minus 1 is attained by f somewhere. Okay, in fact, that somewhere is this corner. Right, so in this corner, f is equal to minus 1. So we already know that there's a place where f is below 0, so it's below the xy plane here. Okay, but right now our largest value of f that we found is 0. Okay, let's see if we can find higher on this region. Okay. All right, what's the next? Let's look at the next piece. So let's look at the behavior of this function on the right side of this square, so on L3. So on L3, what is true? Well, on this piece L3, x is the same. It's actually 1. Right? X is equal to 1 on that piece. And y goes between 0 and 1. Okay. All right. So then f xy is xy minus x squared. Since x is 1, I'm going to replace both of those with 1. Y is just varying between 0 and 1 here. So this is y minus 1 on L3. Well, where does this have its max value? Well, it's going to have its max value when y is largest, and that's going to be when y is equal to 1. Right? So, of course, this is not always going to be true. The reason why this is going to have its max value when y is largest is because this is this linear thing, right? If this were, like 1 over y or something, then it's going to have its max value where y is smallest, right? This is just for this particular form of f here. So its max value is 0. Right? And this occurs at y equals 1. And its min value is minus 1. And this occurs at y equals 0. But we already knew we were going to have a y equals 0 here. Because where is this? When y is equal to 0 here, we're still at this corner. Right? We already found that the value of f at that corner was minus 1. So this is just agreeing with what we found before. But the value of f at this corner is 0. Okay, when x is equal to 1 and y is equal to 1, that's this corner, the value of the function is 0. The value of the function is 0 here. It's actually 0 everywhere on this left edge. Okay, and so on. Okay. So now we just have one more piece to look at. So what about the top on L4? Well, on L4, x varies between 0 and 1, and y is equal to 1. Okay, and so what does f look like? So f of xy is xy minus x squared. If y is equal to 1, this becomes x minus x squared on L4. So now we have arrived at a function that we can't just look at and find what its max or min is. I have a function, x minus x squared. on a closed interval, since y is fixed. We have a closed interval, 0 to 1. I have a function of a single variable on a closed and bounded interval. Okay, how do I find its max and min? Well, this is a Calc 1 problem, right? This is the Calc 1 problem, right? This is our Calc 1 optimization problem. And so what do? I need to think of this as, a function, big F, x minus x squared, on 0 to 1. And I need to apply what I would do in Calc 1 to this. So what would I do to find the max and min here? And take the derivative, right? I take the derivative and say, oh, well, this is 1 minus 2x. Okay, I would set this equal to 0. Right, so 1 minus 2x equals 0 implies x is equal to 1/2. So something can happen there. Now, this something, I could do the second derivative test so I don't have to test any intervals. So let's take the second derivative of f. This is minus 2. That's always negative. So f double prime of 1/2, for instance, is negative. This is a critical point, though. What does that mean? So there's relative max for f at x equals 1/2. And so if I want to know what the max or min value of this thing is, all I have to do is check this critical point. I didn't have to do this. I did this just for fun. Or I check the endpoints. Or not or. I have to check both. Okay. And so I do that. Well, at f of 0 is 0. Right? Big F of 0 is 0. And big F of 1 is 0. Right? But what's big F of 1/2? This is 1/2 minus 1/2 squared. That is 1/2 minus 1/4, which is 1/4. And so, what this means is that f has a max value of 1/4 at x equals 1/2 on this last piece, L4, the top. And f has a min value of 0 on L4. And that occurs at both x equals 1 and x equals 0. So it occurs at the corners. Okay, so let us go all the way back. And we say, okay, so here's my function f. Here's what my region looks like. At this corner, f is 0. At this corner, f is minus 1. At this corner, f is 0. At this point right here, f is 1/4. And at this point, f is 0. Okay. Now, among all those, right, just tracking, 0 minus 1, here's 0 minus 1, that's the same corner. 0, of course, entirely on the left. That's what we started out with. And on the last piece, it's equal to 1/4, 0 at the other two endpoints. So what is the global max for f on R? 1/4. What's the global min? Minus 1. So therefore, f has global max on R at the point y equals 1, x is equal to 1/2. Sorry, literally the opposite thing. There, I swapped my x and y. So at 1/2 1, global max value is 1/4. F has global min on R at the bottom right corner, right? So 1 0. And the global min value is -1. Now you see how much effort we had to go through to find this global max and global min on the boundary, right? And I should point out that this region, this particular region, is pretty much as simple as it gets. All right, it's unit square. In general, my region might look like this. Right here could be my region R. So I can't break it up into these easy linear pieces. It's some curve, right, in the plane. So how could I possibly deal with that? So here's where Lagrange multipliers come in. Okay, so Lagrange multipliers. These are the things that allow us to find global extreme values on the boundary. Okay, so this is what lets us find global extrema on the boundary of some region. Okay, without this, it's pretty much undoable for us. Okay. And so, what is the statement? Okay, what is the theorem? So, theorem. Okay. Let f and g be differentiable at x naught, y naught. Okay. Let c be the level curve that's given at g of xy is equal to constant. Okay. And suppose that x naught, y naught lies on g. Lies on C, this level curve. Okay. Assume that this level curve C is smooth. We know what it means for a curve to be smooth, right? Thanks, chapter 12. And that x naught, y naught is not an endpoint. Okay, of C. All right, this is the setup. If the gradient of G at x naught, y naught is not the zero vector, and if x naught, y naught is a global extreme value for f on this curve C, or I shouldn't say a global extreme value. The value is actually the value of the function at x naught. So if a global extreme value for f happens at x naught, y naught. So maybe that's a better way of stating it, but I don't want to rewrite this. So basically, if a global extreme value for f here, I'll do that. I will rewrite this. So if a global extreme value for f on C occurs at x naught, y naught, then there is a number, lambda, such that the gradient of f at x naught y naught is equal to lambda times the gradient of g at x naught y naught. This is the big important statement. Okay. Now, intuitively, what is this saying? It's saying that under these conditions, the two gradient vectors for f and g are parallel, right? Means that they are scalar multiples of each other. And this scalar multiple that makes these things parallel is called lambda. Of course, lambda is the Greek letter for L, and so it's lambda for Lagrange here. So this is the Lagrange multiplier. Okay, this lambda is the Lagrange multiplier. That's where the name comes from. Now, big question. How does this theorem help me do what I want to do? Okay, so big question. How does this help? So the answer here is that I can assume, right, that in all these problems that I'm going to be working on, I'm going to be dealing with typically a smooth function defined on a closed and bounded region. So by max-min theorem, I can assume, right, so typically, by max-min theorem, I can assume that f has global extrema somewhere on R. Okay, which could include the boundary. So if it occurs on the boundary, del R, of course, in the plane, if this is my region, R, what's del R? It's this boundary curve. So I have del R. This boundary curve is going to be expressible as some level curve, g of xy is equal to a constant. Okay, so I write this in the form g of xy is equal to constant. Thus, if it occurs on the boundary, it must satisfy the Lagrange multiplier equation, which I just wrote, which is the gradient of f is equal to lambda times the gradient of g. Okay. All right, well that's great, but again, how does that help? What am I doing here? What is the process? Okay. So, first of all, this is the process not just for finding global extrema on the boundary, this is the process for finding global extrema for the function, period. So going back, we know, right, by the analog of this theorem that we knew in Calc 1, that wherever, like if f is going to have a global extreme value on closed and bounded region, right, and our f is nice, like our f's are going to be, then this happens somewhere in the interior, right? So it happens somewhere in the interior, right, at a critical point, right, not just anywhere. So at some critical point in the interior, or it happens somewhere on the boundary. Now, if it happens at a critical point in the interior, we know how to deal with that. That's the second partial stuff. Okay, so that's me finding critical points and me just testing, right, all the values, if you like, to do the shortcut here. But finding it on the boundary is what this Lagrange multiplier business takes care of. And so the process here is one, find critical points of f on R. Okay, so those are your candidate points for maxes and mins to occur. Okay, of course, testing whether they're relative maxes, relative mins, saddle points, all that stuff, that's a separate question. So right now I'm just focused on finding global extreme values. Okay, so step 2, set up the equations. Gradient of f is equal to lambda times gradient of g. Use this to exhaustively, this is the key, find points on del r, which is gxy is equal to constant, that satisfy these equations. Okay, so just like in the case of finding critical points on R, you're not guaranteed that anything happens at a critical point. Absolutely nothing might happen at every single critical point you find. Okay, but this is, you think of this as the list of all possible points where something could happen. Okay, so similarly, just because this Lagrange multiplier equation is satisfied at some point on the boundary doesn't mean anything happens there. Just means that something can happen there. And it's the, if you do this exhaustively, if you find every single point on the boundary that satisfies this equation, then what you've done is you have found your full list of candidate points, right? So if something's going to happen on the boundary, that is, if f's going to have a global max or global min on the boundary, it would have to be at one of those points. It might not be at any of those points, but it would have to be at one of them. And then lastly, 3, test all points. And what we mean by test all points is we plug them into the function. We see what the largest value, what the smallest value is. Okay. All right, I think we have enough time to do a single example where we follow this process. Let me pick one that's not too involved. As you'll see, these Lagrange multiplier problems can get really nasty pretty quick. So let's do one example. Like I said, I believe we have enough. You are going to be confused by number 2 at first, because what we mean by exhaustively, it's going to rely on us making a lot of arguments. Picking values of x, solving equations. Picking values of y, solving equations. Picking values of lambda and solving equations. So you'll see exactly what that is. Okay, here's my example. Okay, so let f of xy be the function x squared plus 4y cubed. Okay, find the extreme values of f on an ellipse. Let's just skip straight to it. Actually, no, I'm going to make this a little bit harder. So find extreme values for f on the closed elliptical disk that is x squared plus 2y squared is less than or equal to 1. And the points at which they occur. Okay, so what does our R look like here? So our R is a closed elliptical disk. All right, so here's my region R. The boundary curve, right, del R is what? So here's my closed elliptical disk. What is the boundary curve? Well, it is x squared plus 2y squared is equal to 1. That's my boundary curve. That's this ellipse. Okay. The region R is that ellipse and everything inside of it in the plane, but del R itself is this ellipse. X squared plus 2y squared is equal to 1. So what am I doing here? I want to view this as g of xy is equal to a constant, and so I define g of xy to be x squared plus 2y squared, so that I can recast this as g of xy is equal to 1. Right? Okay, so there's my g of xy. Now, I want to find extreme values for f on the closed elliptical disk. So I'm finding it on this whole region. So first things first, I got to find critical points for f. So let's do that. I compute x and y partials. So the x partial of f is 2x. The x partial of 4y cubed is 0. The y partial of f is 12y squared. Okay. Right, because the y partial of x squared is 0. And so setting this equal to 0, right, setting the gradient of f equal to the 0 vector tells me that 2x is equal to 0, but simultaneously 12y squared is equal to 0. First equation means x is equal to 0. Second equation means y is equal to 0. So it means that 0, 0 is the only critical point of f. Happens right here. Right? So there's a point where something can happen. It's really easy to test this point. I plug 0, 0 into f. I see that it has value 0. Right? So f, note, f of 0, 0 is equal to 0. We can already quickly see that. Okay. And so if I find any values of f that are greater than 0 that lie on this region R, then I found something that is, this can't be a max in that case. If I find value of f that is less than 0, this can't be a min. Right? Okay. Now, the only other place where something can happen here, because this is the only critical point, the only other place where something can happen is on the boundary. And to take care of that, I need to do this Lagrange multiplier business. Okay, remember, the Lagrange multiplier equation, or gradient of f is equal to lambda times gradient of g. Okay, I've already computed the gradient of f. There's the components. Now I need to compute the gradient of g. All right, so what's the gradient of g? So gradient of g, well, let's just write it as the x and y partials of g. So what's the x partial of g? This is just 2x. What is the y partial of g? Well, the y partial of g is 4y. Right there it is. Okay. Okay. And so, writing out these Lagrange multiplier equations, what do I get? I get gradient of f is equal to gradient of g, which means x partial of f is equal to lambda times x partial of g. Y partial of f is equal to lambda times y partial of g. So maybe I'll write that out. All right, what these equations are is x partial of f is equal to lambda times x partial of g, and the y partial of f is equal to lambda times the y partial of g. That's the equations I get. I can actually write those out, though, because I've already computed these things. Right? And so what equations do I get? I get 2x is equal to lambda times the x partial of g, which is also 2x. And I get that 12y squared is equal to lambda times the y partial of g, which is 4y. Okay, so this is the equation I get. Okay, now is where the analysis that you haven't probably seen before comes in. Okay, so how do I solve equations like this? It's 2 equations and 3 unknowns. Right, what does that mean? It means something's got to give in terms of how we're going to find solutions here. I'm going to rewrite that equation. So the system of simultaneous equations is 2x is equal to lambda times 2x, and 12y squared is equal to lambda times 4y. Now, how do I go about solving something like this in general? Okay, well, the idea here typically is, so first of all, again, you're taking partials here and using those to form equations. You can basically get any sort of nonsense coming out of this, right? So there's no completely 100% systematic way to do this because it really depends on those partials that you compute, okay? But generally, the approach here is to start with the equation that is easiest. Okay, start with the equation that's easiest for you. All right. So what is that? Well, ignoring the fact that this has a square term and the first equation doesn't. The first equation is easier just because what occurs on the left and right are very similar to each other, right? So if I look at this thing first, what do I get immediately out of this? 2x is equal to some lambda, some real number, times 2x. When can that happen? So someone asks, so we're solving for lambda. Not really, right? We're solving for x and y here. So then what is the lambda? Well, the lambda is kind of just an obstruction to us solving for x and y. It's some real number. Okay, sometimes we're going to be fixing that real number. What do I mean? Well, look at this equation. What does this equation mean? Try to come up with in your head when this equation would be satisfied. There's one really stupid way to satisfy this equation that makes this very easy. Does anyone see a choice of x I could make here that makes this all work out? Right, regardless of what lambda is. So here's a better way of saying it. Let lambda be square root of pi, right? So let lambda be the square root of pi. Can you still find a solution to that equation that I've circled here, even if lambda is square root of pi? If x is equal to 0, yeah. If x is equal to 0, it doesn't matter what lambda is, right? Then I get equality there. All right, so what does this mean? This means that x is equal to 0. That's a possibility. Okay. But what if x is not equal to 0? Or something else must happen. Now, if x is not equal to 0, let's say that x is equal to 5, right? If x is equal to 5, what does that equation become? It would become 2 times 5 is equal to lambda times 2 times 5. So 10 is equal to 10 lambda. Well, is that equation ever true? Yeah, it is. But only for one single particular value of lambda. Right. So either x is equal to 0 or lambda has to be what? Lambda has to be 1. Right. Notice, if lambda is equal to 1, I get 2x is equal to 2x. That's true for every x, whether x is 0 or not. Right? But if lambda is not equal to 1, if lambda is equal to 17 square root of pi, e to the pi, right? E to the pi to the root 2. Then it doesn't matter because x could still be 0 and make this equation hold. Okay, but these are the only two possibilities. Either x is 0 and lambda can be whatever, or lambda is equal to 1 and x can be whatever. Okay, so you get two possibilities here. Now, the way that this goes is I must chase every possibility, right, to all the way to the end, right? I must exhaust every possibility that I get at every step. Okay, and so that is what I plan on doing. So how do I do that? Well, let's start with the step of exhausting the x equals 0 case. So here's the case that x is equal to 0. Well, what would you do with this typically, right? If you were solving a system of equations like maybe you're more used to from basic algebra, what would you do? You'd say, okay, x is equal to 0, so I can plug that into the other equation. But in the other equation, there is no x. In fact, the other equation doesn't depend on x at all. So how does knowing that x is equal to 0 even help you? You can't plug it back into the equation you started with, because then you're just going to get 0 is equal to 0. That's not going to help you. Right? So what do I do here? Well, there is another equation that has to be satisfied. It's not just these two equations. There's another one. Right? Let's go back. In my setup, what must be true is also on the boundary, g of xy must be equal to 1. That is, I must have this condition, x squared plus 2y squared is equal to 1. Right? So recall, x squared plus 2y squared must be equal to 1. This is g of xy is equal to 1, right? Okay. So x squared plus 2y squared must be equal to 1. Okay. Knowing that x is equal to 0 then tells me what? Knowing that x is equal to 0 tells me that 0 squared plus 2y squared is equal to 1. Or that 2y squared is equal to 1. Which tells me that y squared is equal to 1/2. Which tells me that y is equal to plus or minus 1 over root 2. And so, if x is equal to 0, I get two candidate points that satisfy these equations. What are those candidate points? 0 and plus minus 1 over root 2. Okay. So I get 2 points that are candidates for something happening. Okay. But what about the lambda equals 1 case? Right, so I exhausted the x equals 0 case. If x is equal to 0, then it automatically tells me, because of this constraint here, that y must be equal to plus minus 1 over root 2. And that's what's beautiful about this, because we're thinking of it geometrically, right? We're thinking of optimizing function on some region in the plane, and the constraint that we're interested in question is this g of xy is equal to 1, which is the equation for some boundary curve. But a lot of the times when you see Lagrange multipliers coming up, it doesn't happen geometrically, even though if something geometrically is going on behind the scenes, it happens in the context of some problem about optimizing relative to a constraint. So maybe the function in question is describing like a some kind of like production function, and you have some constraint on the x and y. So the x and y's are like telling you amounts of material that you have to use. And the constraint, this constraint function g, is telling you some logistical constraint on those quantities x and y. And so Lagrange multiplier stuff can be applied just as equally to that as the problem coming from this more geometric picture. Okay, when lambda is equal to 1, what can I say? Well, that's the thing, right? If lambda is equal to 1, using the first equation is going to do me no good, because I'm going to get 2x is equal to 2x, which tells me nothing. That's satisfied for every x, so that's not going to nail down anything. But when lambda is equal to 1, looking at the second equation, I get 12y squared is equal to 1 times 4y. So 12y squared is equal to 4y. All right, so dividing both sides by 4 and moving y to the other side. So this is 3y squared minus y is equal to 0. Factoring, this is y times 3y minus 1 is equal to 0. Okay, what do I get here? I get y is equal to 0, or y is equal to 1/3. Okay. Each of these, right, yields a different possibility that must be investigated. So y is equal to 0 must be investigated. What happens when y is equal to 0? I can use my constraint, right, to find x. So x squared plus 2 times 0 squared is equal to 1, which means that x squared is equal to 1, which means that x is equal to plus minus 1. So that's what I get there. What does this give me? This gives me 2 points, plus minus 1, 0. So there's 2 candidate points I get from the case when y is equal to 0, but that's not exhaustive. I need one more case to consider, y is equal to 1/3. So what about y is equal to 1/3? Well, this means that x squared plus 2 times 1/3 squared is equal to 1, which tells me that x squared plus 2/9 is equal to 1. 1 minus 2/9 is 7/9. And so this tells me that x is equal to plus minus the square root of 7 over 3. Right? And so I get 2 points out of that, plus minus square root of 7 over 3, and 0. And now I have exhaustively finished. Students always ask, how do I know when I'm done? How do I know when I've found everything? I trace back through, right? The first equation tells me exhaustively that there are only two possibilities. X is equal to 0 or lambda is equal to 1. If x is equal to 0, by the constraint equation, y must be plus or minus 1 over root 2. There's no other possibilities. So I get exactly 2 points here, right? There is another possibility, which is lambda is equal to 1. After I fully investigate this, then I'm done, right? I've solved this, okay? And so, here, right? If lambda is equal to 1, then plugging this into the second equation here I got from this Lagrange multiplier business, I get this quadratic equation here, which I can easily factor. When I factor this, I find that y is equal to 0 or y is equal to 1/3. I have to do both of these branches. When y is equal to 0, x must be plus or minus 1, so that's all I get. And when y is equal to 1/3, x must be plus or minus root 7 over 3. So out of this entire process, I got 6 candidate points. 0 plus minus 1 over root 2, plus minus 1, 0, and plus minus root 7 over 3, 0. Now I have to test all these. Right? So the test, right? I test all these points now. Okay, so let's test them all. So first of all, I had my critical point that I test, right? So let's write my function so that we don't forget. What is f of xy? Where did I actually write my function? Oh, here we go. So f of xy is equal to x squared plus 4y cubed. Okay. So I test all my points. First of all, I had my critical point that I test. See what happened there. So f of 0, 0, where is that? So f of 0, 0, that is 0 squared plus 4, 0 cubed. That's 0, okay? And I'm looking for largest or smallest values. Now, let's go through my candidate points. I had 6 of them, right, coming from the Lagrange multiplier business. So 0 plus minus 1 over root 2, plus minus 1, 0, and plus minus root 7 over 3, 0. Okay, so let's do f of 0 minus, or we'll do plus 1 over root 2 first. So what is this? This is 0 squared plus 4 times 1 over root 2 cubed. So 1 over root 2 cubed is 2 root 2 in the denominator here, so this is 4 over, it's 4 over 2 root 2, which is 2 over root 2, which is root 2, right? Okay. F of 0 minus 1 over root 2. You might say, why are you simplifying this at all? Well, in this case, it wouldn't have mattered, but for these, the reason why to simplify is to make it clear which is the larger value and which is the smaller value. Okay. Oh, someone was saying these points here. Yeah. So this should have been, since y is equal to 1/3 here, this isn't 0. This should be 1/3. Yeah. Okay. We would have figured that out at this step, and I'll show you why. The only thing that's changed here is I'm cubing this, so I have a minus sign here. So the only difference is this would have a minus sign out front. So this is actually minus root 2, right? Just from that. What's nice about the rest is I can be really, really nice and efficient here because I'm squaring the rest, and so the plus and minus signs don't matter, right? So here I have plus minus 1, 0, and I have plus minus root 7 over 3 and 1/3. So I'm squaring both of those things because the x slot gets squared while the y slot gets cubed. So this is a f of plus minus 1, 0, so I can do that at the same time. So this is going to be plus minus 1 squared plus 4 times 0 cubed. So that is just 1 in both cases. Okay. And then lastly, f of plus minus root 7 over 3, 1/3, is plus minus root 7 over 3 squared. Okay, plus 4 times 1/3 cubed. So this is plus minus root 7 over 3 squared. This is 7/9. Right, plus 4 times 1 over 1/3 cubed is 1 over 27. So this is 4/27. So this is 21/27 plus 4/27. This is 25/27, which is less than 1. So this can't be the max, and it's not as small as minus root 2, so it can't be the min. So this gets tossed out. In a lot of these cases, if the algebra is too nasty, you can actually rule them out using an argument like this. So I know that nothing happens at either of these points. Here I look at this, and actually, what is my largest value here? So I've tested everything. I've tested all 6 of the points I got from the Lagrange multiplier method, and then I also tested my critical point 0, 0. And so what did I find? Largest value happens here. So this is the largest value. And smallest value is here. And so f has a global max at 0 and 1 over root 2. And the global max value, so its value is root 2. And f has a global min at 0 minus 1 over root 2. And its value is minus root 2. This is the easiest possible Lagrange multiplier problem. You will never have a Lagrange multiplier problem easier than this one. Yours will always be harder than this one. So this is as easy as it gets. Okay. Looking at this picture, right, I can actually identify, right, the points where f has something happening. So there's a critical point here, but it doesn't have a global max or global min. Whether it has a relative max, relative min, saddle point, whatever, you can test that with the second partials test, which I wasn't asked to do, so I didn't do it. So then it has a global max at 0, 1 over root 2. That's here. That's on the boundary right there. And its global min happens here. Okay. Later on, so after we come back from break and I give you guys your first MATLAB assignment, you're going to be plotting some stuff in MATLAB. So you're going to be plotting functions that look like this on regions like this, so you can actually see this behavior and what it is that's going on and why something would look like this. Why we would have a function shaped in such a way that it has its global max, here, and its global min here on the boundary. Anyway. That's it. So you all have a good break. I'll upload some examples over break. Apart from that, when you get back, I'll post your second exam, which will cover all this chapter 13 stuff, okay, all the way up through Lagrange multipliers. So that's the deal. So I'll see you all when you get back.